In this video, we're going to talk about pointers. Pointers are a very important feature in C++. So memory management in general, so the ability to directly manipulate the system memory is what makes C++ such a powerful language. But with that power comes a lot of risk. So it certainly can be dangerous and unpredictable and cause your programs to act strangely or crash or do other bad things if you don't use your pointers correctly. So it's important to take care when you're dealing with pointers. Okay. So when we're talking about pointers, we want to start with the idea of variables in C++. So if I would do like an int x here, this is not like a variable in math. It's not an unknown. So variable is kind of a misnomer, which I talked about before. What x is a label for something that's stored at some memory address. Okay. So if I say for like x or int x is equal to 10, let's say. So somewhere in the system's memory, when you go to execute the program, when you run the executable, the OS is going to allocate a certain block of its total memory to your process. Okay. So when we say int x equal 10, the compiler, as it's running, will find memory that's currently given to your process and put an int size container there. Ints are typically 4 bytes. So it's going to make a 4 byte contiguous memory block that it's going to call X. Okay. So that becomes transparent to the user. I can see out X and it's equal to 10. So if we wanted to see what address happens to be stored or where it happens to be stored at, we can use the address of operator. So the address of operator is going to be the ampersand. So I can do a cout here of ampersand x. Okay, and that will tell us when I run the system where in the system it's being stored. Okay, so let me actually type to do that work. Don't know. Let's try it. It's behaving weirdly, but okay. So if I run this now, you see that gives us this memory address. And memory addresses are in hexadecimal, and they always start with the 0x. The 0x is not really there. That's just a label, so we know. And then it's going to be a series of numbers. They're hexadecimal, so it goes up through F. So A is equal to 10, B is equal to 11, all the way up to F being equal to 15 and base 16. We don't care about any of that. We just care that that's the address currently. Okay. If I run it again, note that I get a different address. The first part's the same for a little bit. The 7FFF is the same, but then it goes totally different. So you can never guarantee that memory is going to be the same from time to time. So here's the concept again. Let's go over it again. So we have this box somewhere in memory. The last time it was this 7FFD6 7274704. That memory address and the next, so that and 4 bytes starting there are reserved for us. And our program put a 10 inside of that. So if we wanted a variable to capture that address, that's what a pointer is. So I can create a pointer variable as follows and say int star p. Now, p is what we would call a pointer to an integer. It's important that we know what type it is because we can do things later with like integer arithmetic and we can add values to this, add one to this. It's going to take it over the size of the data structure we're doing. Okay, so that's why we have to say int star. Note that usually that and that all work. Okay, so it doesn't really matter where you place it, but usually I'll put the star right next to the variable. Okay, so this variable as it stands doesn't point anywhere. And if I would try to do something with it, if I would cout see out X, and let's see out P. And if I would run this guy, we're good. Okay. It gives us this random address here. Okay. Which is really weird. I ran this early and it did not. It shouldn't give us that random address. It can't be counted on to do that. It often, in fact, the time I guess, oh, I guess what it did, because I printed that second, it just set P to 1,000, which is weird. Which is not any kind of address, but it didn't give us a segmentation fault. I bet if I ran this enough, it would, why would it always be that? That's really strange. The other address, but that's always 100, not 1,000. I have to think about that one because before it was giving me an error when I did that. In general, it's not a good idea to have pointers that are not initialized. So we can set it equal to something. So I know I can get to the address of X like that. Okay. So now when I've done that and run it, okay. I don't that hundred's coming from someplace weird. I'm not sure. That's strange. Or the 10 is. We're printing out what's in there, I guess. But the 0x, that's the address that we're pointing to with X. Okay. So that's where the 10's coming from. Oh, I'm printing that address first. Okay. So that's going to set the address to P is now set to the address that X is stored in because of this line. Okay. Once I have that, I can find out what's at that address right now by dereferencing. Okay. So I can say star P, and the star P should be the 10, and it is. Okay. So the memory address looks like this guy here. And notice these two were the same. Okay, so this was the address of X, and this is the P that we set equal to that. Okay, and that was printing out X. This time I printed out the dereferencing of P and got 10 as well. So one issue that we can run into here is one of aliasing. So we sometimes get things that we don't expect. So what that would be, for example, if I were to say cursor here, if I were to say up here, once I've done this, that star P, and I've got it right here, star P is equal to 20. Okay. And then print out star P. Okay. I've got the syntax correct. Yes, it gives us a 20, which we expect, right? So I'm just saying here the star P is now equal to 20. Here's where things get weird. If I see out now X, CX is also 20. So that's where the aliasing comes in. So once I've set this line here, whenever I change this pointer, what the pointer points to, I'm changing X. And that's something we don't think about. So you got to be careful with that. Okay. So if you're going to create a variable that you can do something with later, a pointer. So let's say I do a Q. That's a pointer to an int. I can set it equal to null PTY. Okay. And when I do that, but that's really PTR, but that's, yeah, null PTR. That's it, null pointer. If I set it to that, then it doesn't point anywhere, and it's not going to give me the segmentation fault that I was getting before, but I'm not for this time. Okay. So that's the basics of what a pointer is and how it works. So we use the asterisk when we're declaring it. We use the ampersand to get the address of another variable. And then we use the asterisk again to dereference that pointer and tell us what's stored there. Okay. So note that we can create pointers to not just the built-in data types, but to classes and structs that we create. So if we have the following, we have a struct, student type, and let's say it has a char name, so it has a C string. It has a double for GPA, and it has an int for the student ID. Let's say it has a char for grade. Okay, so if that is the struct that we've developed, okay, if I want to declare a student type object, I would start with student type. And we're still leaving the default constructor, which doesn't put any value anywhere. Okay, call it student, and that would create a student type called student. Okay, if I wanted to create a pointer to a student, I would say student type star student PTR, let's say, for pointer, the address that student, the object we just created, is stored in. Okay, so now I have a student object called student, and I have a student pointer that points to the address of that student object. Okay, so if I wanted to use a pointer to get to the GPA of a student, for example, I could do the following. I could do the star student pointer. Okay, so I'm dereferencing that dot GPA is equal to 3.9. Okay, I need these parentheses because if not, the star wouldn't apply appropriately and it wouldn't work. Okay, so as we'll see more, especially in data structures, you could also here do the following: this little arrow, which is the dash greater than. That would also work. In this case, I wouldn't need that. Okay. So those are the two ways that we can get to that bit of data. Okay. So we can also use pointers to create dynamic variables. Okay, so let me go ahead and get rid of some of this stuff, clear some room here. And just so you understand what I'm saying, these are dynamic variables. And they are basically created during the program execution. Okay, so they don't exist until the program executes. So there are two operators here we're going to use. We're going to use the new to create the dynamic variables, and we're going to use the delete to remove. Okay, so the new is basically going to allocate memory, and the delete is going to deallocate memory. That just means if memory is allocated, then it's being reserved by the operating system. When it's deallocated, it's free for use. Okay, so this new operator functions in this way. If we want to create some new variable, we could just say new, the new keyword, and whatever the data type is, like new int x. Wanted to do that. Okay. We could say new int x10 if we wanted to create a dynamic array. Okay. So the new operator will allocate memory of that designated type and return a pointer. Okay. So that's how that's going to work. So let's take a look at some actual code that works. Okay. So if we have the normal statements that we've done before, so we have an int star p, and we have a char. Semicolon there. We have a char star q. Okay, those are not going to actually create any memory. Okay. Just like if I were doing int x, it doesn't allocate any memory until I do something with it. Okay. So if I were to say something like now p is equal to ampersand x, there's still no memory allocated because we don't have anything real. Okay. If on the other hand, I would say something like p is equal to new keyword type int, now p is a pointer to an integer and p has value. Okay, so it creates the variable during program execution. It doesn't exist until this line. It's going to store the address of that allocated memory in pointer p. Okay. Note this variable has no name, so I can't point to anything else, but I can get to it using the star p is equal to 5. Okay. So in this case, there is no x, there is no variable. All we have is the pointer. Okay. And then once we've done that, and we've done whatever we want to do, okay, we're going to want to be able to delete that variable. Okay. So let's talk about why deleting is important. So if I have my int p, and then I say that star p is equal to 54, actually p here. No, that's what I want. I first have to, I'll get it straight here eventually. I first have to say that p is equal to new int. So I'm allocating memory for p, and I'm setting its value to 54. Okay. That's some memory block. Let's call it 100. Okay. Now I'm going to come back again and say p is equal to new int again. This will allocate some other block of memory. Let's say it's at 200. The new keyword always allocates new memory. And now I say star p is equal to 73. Okay, so we've overwritten the 54 with the 73, kinda, but we haven't really. So now that 100, which we said was this first address of P, it has 54 in it, but there's no way to access it. So that's what's called a memory leak. So that we can't use that memory and it can't be allocated for anybody else. So that's a problem. So what we do is the delete keyword. And what delete will do, delete will deallocate the memory that P points to. Okay. So here, if I were to say delete P, then that memory is freed up. Okay. So if what I'm deleting instead is an array, and you can create, right here, I could have said this, and that would have created an array of 12. Okay. You then put and this is weird syntax. You then put the brackets there. Okay. And that would delete that array. So what else can we do with pointers? So there are several things we can do with pointers. So we have our pointer here. We don't care. We can start over again. We can assign them with the equals operator. So if I have int star p, let me go ahead and do an int x is equal to 10. And then I can do my int star p is equal to the address that x is stored at. Okay. Then I could do int star q and say q is equal to p. So now we have q and p that both point to the same memory address. But there's a problem with that. And the problem is that p and q are both the same. So the aliasing problem we saw before. So if I change what p points to, it also changes what q points to. But even worse, if I were to delete p, it also deletes q. So you have to be careful. So we can also do addition on pointers, which can be unpredictable, but sometimes it makes sense. So if I have, again, my int pointer is equal to that, if I were to say something like plus plus p or p plus plus, either one, it's going to go to p's memory address. It's going to move it over 4 bytes because it's an int. Okay. And this is how arrays work. That's why we always start our arrays at position 0, because the array is a memory address. And then we're adding that subscript that we send for the array, we're adding that to the pointer however many times it says. Okay. So we can also subtract pointers. We can test for equality with the double equal sign, all those things. But pointer arithmetic gets tricky quick, so you got to be careful. So pointers and functions. So we can send pointers as parameters to a function, either by reference or by value. We're going to do an example of both. So we have a void function, call it pointer parameters. We're going to start with an int star, putting the star here this time, ampersand p. Remember, the ampersand means by reference. The star means that it's a pointer. So this is going to send the pointer p by reference. So the address of pointer p. Okay. Or if we just wanted to send it by value, we could just say double star q. That sends a pointer to a double called q. Okay. Pretty basic. If we want to return something from a function, then its type would be int star. That will return a pointer to an integer, which you can do. Okay. So when we create these dynamic variables, so every time that we use the new keyword, we're going to eventually need to use a delete to get rid of it. So that becomes a problem. We have to do it manually, or if we have to do it manually, we may forget. So if we have a class where one of the member data is a pointer, then we have to, well, then we want to automatically get rid of that data. So that's where the idea of a destructor comes in. So we mentioned destructors a little bit, but let's take a better example. So the constructor or constructor, I'm trying to emphasize it more than I would normally say, the constructor, we'll say, of a class is a function with no return type that has the same name as the class. A destructor, same as a constructor, except that it's prepended, or it starts with the tilde character. The tilde is a little squiggly line that on my keyboard at least is the key above the tab key. Okay, so let's take a look at an example of that. So here I have my class, pointer member variable type. It has an int x, an int length of p, and it has a pointer to an int here. So the pointer, we can assign that to anything that we want during the execution of the program. So we want to make sure that it gets deleted. So we're going to create the destructor. The destructor, again, it's the name of the class with a tilde in front of it. It's got to be public. Usually it goes right after the constructor, which we're using the default one here. Okay. We're going to say delete, and we're going to assume that it may have an array. And we're going to erase it that way. It'll be okay either way. But as the note here says, there's a caveat here that this only works when P has a valid value. If P doesn't, it could give a segmentation fault. It could erase other memory assigned to other variables. So it could be really weird stuff going on. Okay, and then down here, you do whatever. We're creating a variable of that. Okay. So the other thing we're talking about in this section with after the destructors is the idea of a copy constructor. So as we've said before, we don't want to just use the equal sign to copy one pointer to the other. Okay. It could create issues for sure. So in the same way, we don't, in fact, I don't try C confuses me sometimes, which is funny since I've taught it forever. When we have an object, we can't just say a new object equals that old one. Okay. So if we have student Bob, I can't say Tom is equal to Bob. Okay. Um, if it's allowed, and I always have to test it because I forget. If it's allowed, it would create aliasing, which is a bad thing. We know that. So what we do instead of that is to use a copy constructor. It used to be when I was teaching this course, we have to create our copy constructors, but we don't anymore. They're created for us automatically. So what the copy constructor does will create a deep copy, we would say, of this. Okay. So the assignment operator equals, I think it does work with objects, but it creates a shallow copy, which means both names point to the same exact address. So a change to one is a change to the other. So instead we can use the copy constructor. So this is what this looks like. So down here, we have this pointer member variable type X, and we can just use this pointer member variable type Y is the new one, send it X as the template. When it's done, X and Y will contain the same data, but they won't be aliased. Okay. And again, if we would have done it this way, if I would have created that works, but we have an aliasing problem in that both X and Y point to the same data, and a change to one would be a change to the other. So the copy constructor, you don't have to make them anymore. They're already built in, but they're going to automatically execute in the following situations. When we declare an object and it's initialized by using the value of another object, as we just did. So I'm using this X to declare my new variable. So these are the parameters I'm sending to the constructor. Use this template to create a new one with the same data. Okay. We also are going to call, it's going to be called automatically when we're going to pass an object by value. Okay. So when if we just did the equivalent of an equals when we sent an object as a parameter to a function, it would be creating an alias, which would be passing by reference, which we're not doing. So the copy constructor will make a local copy of the object when we get inside the function. Okay. We also use it when the return value of a function is an object for the same reasons. Okay. So that's the copy constructor. So another thing that we have to worry about here is back to the problem of inheritance, which we've been talking about for a while. So in C++, one of the features we have, if we have a function that that takes an object of some base class, then we could also send an object of a derived class. So let's just say, I'm gonna do a lot of hand waving here. Let's say we have a class called pet, and it has, some stuff in it, whatever. And then we're going to have a class dog that derives in a public fashion from pet. Okay. So with this, and there's a lot more to that, of course. With this nomenclature here, then the pet is the base class and the dog is the derived class, but a pet is, a dog is a pet. Okay. And then we have some function. Say it's a void function, print pet. And it takes as its parameter a pet p. Okay. And then it does whatever it does. Since a dog is a pet, we could send a dog object to this function and it would be fine. So no issues at all. Okay. The only issue comes up if inside of this function, which is expecting the pet p, we call a function where there's a version in both the superclass and the subclass. Okay. So that's kind of a problem. So we address that problem by creating virtual functions. So we do a virtual void print pet. The virtual keyword is going to mean that the function or that the function's not going to be called until it actual runs. And then it knows. Because we don't know when we create the print pet function, we don't know if it's really a pet or if it's a derived class of the pet. But by making the function virtual, it will check at runtime to make sure that it does the correct version. So the exact version of the function is deferred until runtime. We know what we're dealing with. So we talked a little bit before about the destructors, and it's recommended that whenever you have a pointer member variable, that you have a destructor. A problem can occur if what we just did, where we're passing in an object that's a derived class rather than the base class. In that case, you want to make sure that your destructor is a virtual destructor. That way, it will know to destroy the right stuff because the derived classes often have more things that you need to delete. So by making the destructor virtual, when you have pointer data, okay, it makes sure that the correct one functions. Okay. So again, a virtual function is a function, and we use it when we have only when we have inheritance. If not, there's not a reason to use it. It means that because we don't know when we write the function whether we're going to be getting the derived class or the base class, we put the virtual keyboard and it waits until runtime and it gets called on something. So if I send a dog to this function, at runtime, it knows it's a dog. When I write the program, it doesn't know what it's going to get. But then at runtime, if I send it a pet object, it knows it's a pet object and it calls the correct destructor. So another thing that we need to talk about in our functions is an idea of um, an abstract class or a pure virtual function. So if we were developing a shape class, let's say, I've got class shape, and it's got some private data. Let's say it has a string color. Okay. In the public area, let's say I want to have an area function. So I want to make sure that, and I know I'm going to inherit from this. I know that I'm going to derive a rectangle and a circle or whatever. So as it stands now, if I put area here, I have to put a definition of area. But I can't do the area of this random shape because there's nothing to base it on. So to avoid having to type anything in here, I can do the following. I can make it a pure virtual function. So to do that, I would say virtual, and this is a void function, let's say. It doesn't matter. It could be a double. Area. And then a weird syntax. I think these were solving problems in interesting ways. Equals 0. The equal 0 makes it a pure virtual function. Okay. So what that means basically then is that the shape object, so an object of type shape, doesn't have an area. There's nothing there really. It's undefined. But every time I create something derived from that, so if I were to create class circle public shape, Okay. Circle has the obligation, means it has to create an area function with the same signature. By the same signature, I mean the number and type of parameters. So I would have to create a public double area function. Okay. Same thing if I were to make a rectangle class based on that. So once we've done that, we've just said that a shape has an undefined area function. So that means we cannot create a shape. So I'm just, again, making up lots of stuff. In int main, now, get rid of that stuff. If I were to say shape S, it would give an error. It would say I'm trying to instantiate an object or a class that is abstract. Okay. If I were to create a circle class, but not define the area function, it would give me an error message also saying that I have to define that function. And I can't, I mean, I can have other versions of the function that return voids or whatever you want to do. We can overload them as before, but there has to be at least one version that looks exactly like the one that was declared as a virtual private function. Okay. So some of that gets real tricky. The syntax is weird. It's weird that with pointers that we have basically three operations. We have the dereferencing, we have the declaration of the pointer, and we have um, the address of operator, but we only have two symbols, which gets a little strange. So the asterisk has double duty. It's used when it's declared, and it's used to dereference a pointer. Remember, those memory values are not going to be the same from run to run of your program, so you can't write any code that assumes that. They're consistent within the running of a program. Okay. So then we talked about some other things that we can do, ending up with this idea of virtual functions where the binding to a particular version of the function, whether the superclass or the subclass, is deferred to runtime. And then the pure virtual functions, which have the super weird, granted it's super weird, there's a virtual keyword and the equal zero there. A pure virtual function, only one or more, it doesn't matter, in a class means that it cannot be instantiated. It's an abstract class, but it gives to all of its children. So all of the derived classes from that class have the obligation to have a version that looks exactly like the virtual one. So that's it. There's a lot going on there. So this is tricky stuff. But this is really important, especially as we move on to data structures. So the first thing we're going to cover in data structures is this chapter again, because pointers really are how we create the data structures that we create. So this is a lot to take in. I would read through the book as well. There are lots of examples there. I would watch this video more than once if necessary, and certainly ask questions if needed.